So Llorenc is at the Barcelona Supercomputing Center, worked on the seasonal forecast for wind power.
Okay. Thank you, Robert. And okay, good morning, everybody. Please make signs when it's time. So I'll going to be presenting the seasonal forecasts for wind power that we've been doing in Clean for Energy in the Work Package 1. Especially focusing on the winter of 2016-17, which, if you look at the dates of the project, is an event that happened during the project. So we find it interesting that throughout the project we encountered an interesting event that was interesting to study. Okay, so let's see how the colors look like. Yeah. Okay. So not so bad. Yeah, the blue colors indicate areas where there is lack of wind. Those 4 maps are for October, November, December, and January, so this is a very wide concept of winter. But at least when we work with seasonal forecasting winter, we work with December, January, and February, so February map is not here because the anomalies were not so big in February. But I want you to notice also the green lines, the contour lines that you see there. This is the pressure anomalies, and you see that in all the months there is high pressure systems over Europe, or in the case of November over the Atlantic, which of course are producing the lack of wind, the wind stealing in the region. And it's quite surprising that you see 4 months in a row with such blocking situations. Yeah, it would be great to understand why that happened. Okay, here we have an average for the October, November, December, and you can see that the most impacted area was France, Spain, north of Spain, south of UK, and also parts of Germany. And I didn't say it, but this color scale is a standardized wind anomaly, which means that we compute how many standard deviations we are away from the mean. And in the case of the darkest color, if we are more than 3 standard deviations away of the mean, that's a freaking event, okay? Okay, so this event has had a lot of impact in the energy sector. Of course, the lack of wind resulted in means generation, lack of wind power production. So this impacted the owners of the wind farms. Also, this was accompanied by means precipitations, and there was less water for hydropower production. Also, typically in winter with the blocking situations, we have very low temperatures. This was the case in December. I think it was very cold, and the temperatures increased a lot. There was also an air pollution episode, Robert, I'm right? And finally, power prices, coincidentally with, rised for the high electricity demand. So we see that was an event that meteorological or climatological event that really had an impact on the energy sector as a whole, not only wind power but as a whole. I'll be focusing on the wind power in the next slides. Okay, so we might wonder why that happened. And if we look at the atmosphere as a chaotic system that evolves, it is evolving fast, let's say. From one day to another, the weather conditions change drastically. So if we look at the atmosphere, we might think that it's very bad luck that we have like 4 months in a row with very low wind speeds. It's something that's nearly impossible. But then, if we realize that the atmosphere is not alone in the Earth, we have other components in the Earth system, and that's what climate models try to do. Try to incorporate information from other components of the Earth system, and you have here those components. The ocean is a big heat storage. The sea ice and the snow cover have ability to reflect radiation, and so. We get less energy income if we disperse the radiation. And finally, soil moisture is also important because the uptake by the ground is also important. So all those 4 components that I have here on the right, they evolve much more slowly than the atmosphere. That means if you have high sea surface temperatures in the 1st of January, it's very difficult that you have low at the end of January. So in some sense, these Earth system components are more predictable. We can do predictions at longer time scales. And with this in mind, we have the idea, or at least I have the idea, that these 4 months in a row of very low wind speeds and high pressures are the symptom of one of those components forcing the atmosphere. We really don't know yet what it is, but I want to show another example for you to understand better how that could be working. This is another case study that we did in Clean for Energy. It's a US episode that happened in the first quarter of 2015. Yeah, it impacted a lot of generating companies and so on. And in this case, we already do have some ideas of what caused it. It was a similar case that presented in Europe, 3 months of very low wind speeds. And in this case, in the first picture, you can see the sea surface temperature anomalies. You see very high sea surface temperature anomalies near the US coast. But I don't want you to look at these temperatures. I want you to look at the area that is circled in green. You can see that there are also in the tropics some anomalies, some temperature anomalies, and the it's very good. So the contours here are precipitation anomalies, and you can see that in this case there are like 2 stripes of precipitation anomalies, and that indicates that there was a lot of convection in the area. And this convection is, of course, caused by the high SSTs. The sea surface temperatures produce convection and a lot of rain. And this convection modifies the atmospheric circulation, the general atmospheric circulation. You can see in the bottom the potential height at 200 hectopascals. And you can see that there is this is the anomaly pattern for the period. And you can see that there is a high pressure pattern over the US that is coming from the tropics. So the idea here is that the sea surface temperatures in the tropics during several months were affecting the general circulation and impacted the winds in a very far away area. Okay, so we would like to get to similar conclusions for the European case, but we are not still there. Okay, so let's go into the forecasting system that the service that we set up for the contract. So the idea here, how we can take profit of these slow evolution fields. We instead of using a meteorological or an atmospheric model, we use a climate model which incorporates an ocean model that predicts the sea surface temperatures, a sea ice model that predicts the sea ice cover extent, and so on. And so, forecasting the slow evolution fields and its impact on the fast evolution fields, we can probably get a signal like the ones that I showed before. And also, it's important that when we run these models, we run several ensemble members initialized with slightly different initial conditions so that we get rid of the uncertainty. And that's what exactly what the CMWF system for does. That is the model we are using for the service here. Okay, and if we take the model as it is, as it was mentioned yesterday, the models have biases, and if you want to use an impact model on top of it, it would not work, so we need to bias adjust. The details are ugly, so I will not talk about it. If you want details, I will be happy to explain later. And then another important step, and this is a conceptual step, and this is we need to average the whole season to get a signal. If we look at values hour by hour, we don't get any signal. We need to look at the average values. Then what we do is to present results from the different ensemble members. We distribute all the ensemble members into 3 categories. This is something that we do to simplify the information. If we give users 51 values, well, you will tell us that it is not useful. So what we try to do is to condense information into 3 categories: below normal conditions, or above normal conditions. And then, yeah, we compute the probabilities for each of those 3 categories. In this case, in the screen, you can see a probability distribution function which shows the probabilities for each wind speed, or the density of the probabilities for each wind speed. And in this case, the vertical dashed line is the observation. So that was a very good forecast in this case, with that was suggesting that 71% of probabilities for the below normal category. Thanks, Robert. Okay, let's go to the forecasts themselves for the 2016-17 case. This is a prototype that we have in the BSc website. It is called Resilience. We also have a similar prototype in the Clean for Energy visualization tool. What you can see here is all those dashes are different grid points for the model, and the color and the tilt of the lines indicates the predicted anomaly. So you can see that in this case, the model was predicting negative anomalies. So at first sight, it would be a good forecast. I have to mention that this is a forecast of capacity factors. So this is a forecast not of wind speed, but we have applied an impact model, power curves, to give a forecast that is useful for the industry at the end, or is more useful. So yeah, this is a forecast issued in November 2016 for December, January, February 17. And then if you click into a grid point, you can get the more detailed information for this grid point. For instance, here I clicked on a point in the border of the Netherlands and Germany, and here on the top appears a panel with a lot of information. The more important information that you have to look at the beginning is the skill. Here you have in this point 8% skill. This indicates the quality of the forecasts in the past. We have been evaluating the forecasts in the past to see if they were useful or not, and in this case they were. And on the left you can see the historical values of capacity factor that we modeled during the project, and this is the forecast for the next season, grouped in 3 categories: red for above normal, white for normal, and blue for below normal. And you can see that some of the ensemble members still saw high capacity factors, but most of the members suggested below normal capacity factors. In this case, I think it's 58% probability against 20 and 20. So I think that in view of those forecasts, a user would at least have been prevented that one of those events could be happening. Okay, I will skip this applications slide. And finally, I invite you to stay tuned. You can download the report for the case study at the Clean for Energy website. I also invite you to check the forecasts for at the 2 visualization demonstrations that we have built. And finally, the case study will be further investigated in another H2020 project that we are working at BSc with many colleagues in the room as well. It's called S2S4E, and I invite you to talk to us later in the session at the afternoon. Thank you.
Thank you.